Article 300.3b of the National Electrical Code states that conductors of different systems, voltages, or circuits shall not be grouped together in the same raceway, cable, or other enclosure unless permitted. Article 300.5 states that conductors shall be of sufficient size to carry the current under the applicable conditions. Article 430.72b dictates that the ampacity of the common return conductor, which is the neutral in a direct current circuit, shall be sufficient to carry the sum of the branch circuit currents. Beyond code requirements, ensure that the common return line is large enough to prevent excessive voltage drop. Also, the negative terminal of the power supply should be properly grounded. Based on this information, it is recommended to follow these guidelines. Route the solenoid wiring in a raceway or cable tray separate from other circuits. Use a common return line sized according to the following formula. The ampacity of a common return equals the sum of the branch circuit amperages. The common return line should be at least 14 American wire gauge for a 120 watts power supply. Provide a ground connection for the negative terminal of the power supply. Label the junction box and common return line clearly to indicate their purpose. As an example calculation, assuming each solenoid valve draws 1 amp, the ampacity of the common return line would be calculated as follows. The ampacity of common return equals 5 multiplied by 1 amp, which equals 5 amps. Therefore, a 14 American wire gauge wire would be sufficient for the common return line. The ampacity of a conductor refers to the maximum amount of electrical current that a conductor can carry continuously without exceeding its temperature rating. Several factors influence the ampacity of a conductor, including the conductor material, its size, its insulation type, and the ambient temperature. Conductors made of copper generally have a higher ampacity than conductors made of aluminum for the same size. This is because copper has a lower electrical resistance than aluminum, which means it generates less heat when carrying the same amount of current. The larger the conductor, the more current it can carry without overheating. This is because a larger conductor has a lower resistance, which allows more current to flow through it with less heat generation. The type of insulation used on a conductor also affects its ampacity. Some insulation materials are better at dissipating heat than others, which allows conductors with these types of insulations to carry more current. The ambient temperature, which is the temperature of the surrounding environment, can also affect the ampacity of a conductor. If the ambient temperature is high, the conductor will not be able to dissipate heat as effectively, which will reduce its ampacity. The National Electrical Code, or NEC, provides tables that list the ampacities of various types of conductors under different conditions. These tables can be used to determine the appropriate size of conductor for a particular application. In order to determine the appropriate size of a conductor for a specific application, you need to consider the following factors. Firstly, the amount of current that the conductor will be carrying. Secondly, the type of conductor being used, either copper or aluminum. Thirdly, the insulation type of the conductor. Fourthly, the ambient temperature. Fifthly, any adjustment or correction factors that may apply, such as those for conduit fill or ambient temperature. Once you have gathered this information, you can consult the NEC ampacity tables to determine the appropriate size of conductor. It is always recommended to use a conductor that is larger than the minimum size required by the NEC to provide a safety margin and to account for any future increases in current. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. When electrical current flows through a conductor, some of the electrical energy is lost as heat due to the resistance of the conductor. This loss of energy results in a decrease in voltage along the conductor. Voltage drop can have a significant impact on the performance of electrical equipment. If the voltage drop is too large, the equipment may not operate properly, or it may even be damaged. For example, motors may run slow or overheat, lights may be dim, and electronic devices may malfunction. The amount of voltage drop in a conductor depends on several factors, including firstly, the length of the conductor. Secondly, the size of the conductor. Thirdly, the amount of current flowing through the conductor. Fourthly, the type of conductor material, either copper or aluminum. The longer the conductor, the greater the voltage drop. This is because the current has to travel a longer distance through the conductor, resulting in more energy loss. The smaller the conductor, the greater the voltage drop. This is because the smaller conductor has a higher resistance, which results in more energy loss. The more current flowing through the conductor, the greater the voltage drop. This is because the energy loss is proportional to the square of the current. Aluminum conductors have a higher resistance than copper conductors, so they will have a greater voltage drop for the same length, size, and current. The National Electrical Code, or NEC, recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. A branch circuit is a circuit that extends from the final overcurrent protection device to the outlet or equipment being served. A feeder is a circuit that carries power from the service equipment to a subpanel or branch circuit panel. To calculate voltage drop, you can use the following formula: voltage drop equals current multiplied by resistance. The resistance of a conductor can be calculated using the following formula: resistance equals resistivity multiplied by length divided by area. Resistivity is a property of the conductor material that indicates its resistance to the flow of electrical current. The resistivity of copper is lower than the resistivity of aluminum, which means that copper is a better conductor of electricity. Length is the length of the conductor in feet. Area is the cross-sectional area of the conductor in circular mils. Circular mils is a unit of area used to measure the cross-sectional area of round conductors. To reduce voltage drop, you can use larger conductors, shorter conductors, or conductors made of a material with lower resistivity, such as copper. You can also reduce the amount of current flowing through the conductor by using more efficient equipment or by reducing the load on the circuit. Grounding is the process of connecting electrical equipment and systems to the earth. This provides a low resistance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock and damage. Grounding is an essential safety measure that is required by the National Electrical Code, or NEC, for most electrical installations. There are several reasons why grounding is important. Firstly, it protects people from electrical shock. If a fault occurs in an electrical system, such as a wire coming loose and touching a metal enclosure, the enclosure can become energized. If a person touches the energized enclosure, they could receive an electrical shock. However, if the enclosure is properly grounded, the fault current will flow back to the source through the grounding path, tripping the circuit breaker or fuse and de-energizing the enclosure. Secondly, it protects equipment from damage. Fault currents can also damage electrical equipment. When a fault current flows through equipment, it can generate heat and cause the equipment to overheat and fail. However, if the equipment is properly grounded, the fault current will be diverted away from the equipment through the grounding path, protecting the equipment from damage. Thirdly, it provides a stable reference point for voltage. Grounding provides a stable reference point for voltage in an electrical system. This helps to ensure that the voltage in the system remains within safe limits and that equipment operates properly. There are two main types of grounding systems. Firstly, the equipment grounding system, and secondly, the system grounding system. The equipment grounding system provides a path for fault current to flow back to the source in the event of a fault. This system consists of the grounding conductor, which is a wire that connects the metal enclosures of electrical equipment to the grounding electrode. The grounding electrode is a metal rod, pipe, or plate that is buried in the earth. The system grounding system grounds the neutral conductor of the electrical system. This system helps to stabilize the voltage in the system and to reduce the risk of electrical shock. The system grounding system consists of the grounding electrode conductor, which is a wire that connects the neutral conductor to the grounding electrode. The size of the grounding conductor and grounding electrode conductor is determined by the size of the electrical system. The NEC provides tables that specify the minimum size of these conductors. It is important to properly install and maintain grounding systems to ensure that they are effective in protecting people and equipment from electrical shock and damage. Some common grounding mistakes to avoid include: firstly, using undersized grounding conductors. Secondly, not properly connecting grounding conductors. Thirdly, not properly maintaining grounding systems. And fourthly, not testing grounding systems regularly. The National Electrical Code, or NEC, is a set of standards for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is not a law, but it is widely adopted by state and local governments as the basis for their electrical codes. The NEC covers a wide range of topics related to electrical safety, including wiring methods, overcurrent protection, grounding, and equipment installation. It is divided into chapters, articles, and sections, each of which addresses a specific aspect of electrical safety. The purpose of the NEC is to protect people and property from the hazards of electricity. It does this by providing detailed requirements for the safe installation of electrical wiring and equipment. The NEC is based on sound engineering principles and is constantly updated to reflect the latest advances in electrical technology. The NEC is an essential resource for electricians, electrical contractors, and other professionals who work with electricity. It provides them with the information they need to install electrical wiring and equipment safely and in compliance with local codes. The NEC is a complex document, and it can be difficult to understand all of its requirements. However, there are many resources available to help people learn about the NEC, including training courses, seminars, and online resources. Some key sections of the NEC to be aware of include, firstly, Article 110, Requirements for Electrical Installations. This article covers general requirements for electrical installations, including wiring methods, overcurrent protection, and grounding. Secondly, Article 210, Branch Circuits. This article covers the requirements for branch circuits, which are the circuits that supply power to outlets and equipment. Thirdly, Article 220, Branch Circuit, Feeder, and Service Calculations. This article provides methods for calculating the size of branch circuits, feeders, and services. Fourthly, Article 250, Grounding and Bonding. This article covers the requirements for grounding and bonding electrical systems. Fifthly, Article 300, Wiring Methods. This article covers the requirements for various wiring methods such as conduit, cable, and raceways. Sixthly, Article 400, Flexible Cords and Cables. This article covers the requirements for flexible cords and cables which are used to connect portable equipment to power outlets. Seventhly, Article 430, Motors, Motor Circuits, and Controllers. This article covers the requirements for motors, motor circuits, and controllers. Eighthly, Article 500, Hazardous or Classified Locations. This article covers the requirements for electrical installations in hazardous locations, such as areas where flammable liquids or gases are present. The NEC is an important document for anyone who works with electricity. By following the requirements of the NEC, you can help to ensure the safety of yourself and others. In electrical engineering, a solenoid valve is an electromechanically operated valve. Solenoid valves are used to control the flow of liquids or gases in a wide variety of applications, including pneumatic and hydraulic systems, process control, and medical equipment. A solenoid valve consists of two main parts. Firstly, the solenoid, and secondly, the valve body. The solenoid is an electromagnetic coil that, when energized, produces a magnetic field. This magnetic field pulls or pushes a plunger, which is connected to the valve stem. The valve body contains the valve orifice, which is the opening through which the liquid or gas flows. The valve stem controls the opening and closing of the valve orifice. When the solenoid is de-energized, a spring returns the plunger and valve stem to their normal position, closing or opening the valve orifice. Solenoid valves can be either normally closed, NC, or normally open, NO. A normally closed valve is closed when the solenoid is de-energized and opens when the solenoid is energized. A normally open valve is open when the solenoid is de-energized and closes when the solenoid is energized. Solenoid valves are available in a variety of sizes, materials, and configurations to meet the needs of different applications. They can be made from materials such as brass, stainless steel, and plastic. They can also be configured with different types of end connections, such as threaded, flanged, or welded. When selecting a solenoid valve for a particular application, it is important to consider the following factors. Firstly, the type of fluid or gas being controlled. Secondly, the pressure and temperature of the fluid or gas. Thirdly, the flow rate required. Fourthly, the voltage and current requirements of the solenoid. Fifthly, the environmental conditions in which the valve will be used. Solenoid valves are reliable and versatile devices that can be used to control the flow of liquids or gases in a wide variety of applications. When properly selected and installed, they can provide years of reliable service. A compressor control system is a system that controls the operation of an air compressor. Air compressors are used in a wide variety of applications, including pneumatic tools, air conditioning systems, and industrial processes. A compressor control system typically consists of the following components. Firstly, a pressure sensor. Secondly, a controller. And thirdly, an actuator. The pressure sensor measures the pressure of the compressed air. The controller receives the signal from the pressure sensor and uses it to determine whether the compressor should be turned on or off. The actuator is a device that turns the compressor on or off. There are many different types of compressor control systems available. Some common types include firstly, pressure switch control, secondly, start-stop control, and thirdly, variable speed control. Pressure switch control is the simplest type of compressor control system. In this type of system, a pressure switch is used to turn the compressor on or off. When the pressure in the compressed air tank drops below a certain level, the pressure switch turns the compressor on. When the pressure reaches a certain level, the pressure switch turns the compressor off. Start-stop control is a more sophisticated type of compressor control system. In this type of system, a controller is used to start and stop the compressor based on the demand for compressed air. The controller monitors the pressure in the compressed air tank and starts the compressor when the pressure drops below a certain level. The controller stops the compressor when the pressure reaches a certain level. Variable speed control is the more sophisticated type of compressor control system. In this type of system, a variable speed drive, or VSD, is used to control the speed of the compressor motor. The VSD adjusts the speed of the motor to match the demand for compressed air. This can save energy and reduce wear and tear on the compressor. When selecting a compressor control system, it is important to consider the following factors. Firstly, the type of compressor being used. Secondly, the application for which the compressed air is being used. Thirdly, the desired level of control. Fourthly, the energy efficiency requirements. Fifthly, the budget. Compressor control systems are essential for ensuring the efficient and reliable operation of air compressors. By selecting the right control system, you can save energy, reduce wear and tear on the compressor, and improve the overall performance of your compressed air system.